These are your notes for Unit 5, Day 2 of Pre-Calculus. If you would like to see the warm-up, review question, or any homework questions we covered in class today, just look at the finished notes. So today we're going to talk about exponential functions. We'll talk about how to graph them. We'll talk about how to solve equations involving exponential expressions. We'll talk about the natural base e and how to graph e and how to deal with e. So evaluating exponential functions or expressions. So you could use a calculator to evaluate each of these. And on Desmos, you can use the A to the B button. So you could do 2 and then hit the A to the B button. Oops. The A to the B button and then 1.4. On some of your calculators, it might be an X to the Y button. And on the graphing calculator, it's the caret button, the upside down V. So if you did 2 with the upside down V and then 1.4. So I'm assuming that all of you guys can evaluate all of those on your calculator. So we'll just do a couple of them on Desmos. So if I wanted to evaluate these guys, we have 2 to the 1.4 power. And let's go out 2 decimal or 3 decimal places. So this would be 2.639. So 3 decimal places. And then 2 to the 1.41, we can just put an extra decimal place. This would be 2.657. 2 to the 1.414 power would be 2.665 if I round that up, and so on and so forth. So hopefully you guys are all okay with evaluating exponential expressions on a calculator on Desmos. Let's just review some of the laws of exponents. So if you have 2 exponential expressions and they have the same base, so remember A is the base, M is the exponent. So if you're multiplying 2 terms and they have the same base, you get to add the exponents. So if it was like 2 to the 3rd times 2 to the 4th, you add the exponents and that would be 2 to the 7th. If you are dividing 2 terms and they have the same base, then you get to subtract the exponents. So if it was 2 to the 3rd over 2 to the 7th, this would be 2 to the negative 4 or 1 over 2 to the 4th. So if it's a negative exponent, you can bring it down to the bottom. If you have an exponential expression and it's being multiplied or taken to a power, you can multiply those exponents. So if we had something like 2x to the 4th raised to the 3rd power, you can distribute the 3 to all the terms on the inside to the coefficient and to x to the 4th. Or you can think of it as writing it 3 times. So 2x to the 4th times 2x to the 4th times 2x to the 4th. So this would end up being 2 to the 3rd, which is 8. And then, x to the 4th raised to the 3rd power would be x to the 12th. So that would end up being 8x to the 12th. The next one we talked about. So if you have an expression and the exponent is negative, you could rewrite it as an expression with the exponential expression in the denominator. So a to the negative m is the same as 1 over a to the m. Anything to the first power is itself, and then anything to the 0th power is 1 other than 0. So those are your laws of exponents. So exponential functions. Typically, we've already talked about the exponential function 2 to the x. I believe we graphed that earlier with our parent function. So the base would be 2. And then we graphed it, and it ended up looking like a ramp. Another way to think about an exponential function, and this is more of the real world basis, C is called the initial value, and then A is the growth factor. So you might remember last year when we talked about bacteria problems, the final amount, which we called A, is going to equal to the original amount, which we called P, and then to the rate, so 1 plus the rate, or minus the rate raised to the time. So in this case, P is the original amount. So if it was money, it was the original amount that you invested. And then R is going to be like the growth factor. So if it was increasing by 100%, it would be 1. If it was increasing by 75%, it would be 0.75, and so on and so forth. And so in this exponential expression, C would be your original amount. So it's how much you would have if the time was 0. And then A is how much it's growing each time. So for instance, if we wanted to evaluate 5 and then times 2 to the x, 5 is going to be your original amount. And then 2 is your growth factor. So that means it's doubling every time. So if I plug in 0 for x, so this is my original amount, I would produce a value of 5. So if I plug in 1 for x, 2 to the first is 2 times 5 is 10. If I plug in 2 for x, 2 to the second is 4 times 5 is 20. If I plug in 3 for x, 2 to the third is 8 times 5 is 80, and so on and so forth. How can you tell by looking at the table if an expression will be exponential? So you don't have the equation, you just have the table. What you do is you divide. So you take a term divided by the previous term. So if I took 10 divided by 5, I get 2. And then look at the next set. If I took 20 divided by its previous, I would get 2. Or if you take 40 divided by its previous y value, you get 2. Or if I took 80 divided by its previous y value, you get 2. So a way to tell if a table of values is going to be modeled by an exponential function is you divide the y value by a previous y value. So this would be the next y value, and then this would be the previous y value. So that is one way to tell by looking at a table whether or not a table of values would be exponential. And then if we wanted to graph it, we could just graph on the table. So we're going to go by 10. So 10, 20, 30, 40, 50, 60, 70, 80. And so we have 0, 5, and we have 1, 10, and we have 2, 20, and we have 3, 40, and we have 4, 80. So notice we're making that ramp shape that we made before. So linear, exponential, or neither. So remember, for it to be linear, the change in y over the change in x's need to be constant. So if we look here, my change in my y's, every time they're going down by 3. So my change in my y's is constant each time it's going down by 3. And then my change in my x's is constant each time it's going up by 1. So since my change in y over my change in x is constant, it's -3, this would represent a linear table of values. You could also graph and see if the points are making a line or not. On the next one, this one's 16, 8, 4, and 2, so it's not constant. So then we try the other rule. So take a term and then divide by the previous term. So 16 divided by 32, I get a half. Or 8 divided by 16, I get a half. Or 4 divided by 8, I get a half. Or 2 divided by 4, I get a half. So since all of the y terms divided by the previous y terms are a half, this is going to be exponential. So these points would represent an exponential function. On the next one, I have 2, then 3, then 4, then 5. So this is not linear because that change isn't constant. And then if I took 4 divided by 2, I get 2. If I take 7 divided by 4, I don't get 2. So this is not linear and it's not exponential. All right, so graphing exponential functions, again, we already graphed 2 to the x at some point, I believe. But if I plug in 0, 2 to the 0th power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the negative first power is 1/2, then we have 1/4 and 1/8. So we have 0, 1, 1, 2, 2, 4, 3, 8, and then we have 1/4, or sorry, 1/2, 1/4, 1/8. So we've got our ramp looking shape like that. So that would be 2 to the x. What's going to happen if I graph 1/2 to the x? So anything to the first or 0th power is 1. And then 1/2 to the first power is 1/2. 1/2 squared would be 1/2 times 1/2 is 1/4. 1/2 to the third would be 1/2 times 1/2 times 1/2, which is 1/8. 1/2 to the negative first power. Well, you can distribute that exponent in. It would be 1 to the -1 over 2 to the -1. So you flip them and you get 2. 1/2 to the -2 power would be 4, and to the -3 power would be 8. So we have 0, 1, and then we have 1, 1/2, 2, 1/4, and then 1/8, and then we have -1, 2, -2, 4, -3, 8. And so it's a ramp, but it's going in the opposite direction. So it's decreasing in value over time. So notice if your base is a fraction less than 1, then it's going to decline in value over time, which makes sense because that's the growth factor. So it's not growing, it's actually shrinking by 1/2 each time. So it would be like a half-life formula. And then here, my growth factor was 2, so it's growing by 2 each time, or it's doubling each time. All right, so go ahead and see if you guys can graph both of these using transformations. So pause the video and see if you can use the parent function to graph these two. All right, the first one is you're just going to take that normal exponential and move it 2 down. So this was the original point. So I'm going to move that point 2 down, and it's going to be right here. And then normally, here's my asymptote that my graph won't pass. So I'm going to move that asymptote 2 down, so it'll be right here. And then I'm just going to make my ramp. So it'll look like this and like this. So that would be 2x minus 2. So you would take your original y-intercept. So you're going to want to move the y-intercept, and you're going to want to move the asymptote, the horizontal asymptote. All right, so we have 1/2 x to the minus 1. So remember, this would move the entire graph right 1. So here was my original point. So I'm going to move that to the right 1. And then that's all that's happening. So I'm just going to do this. And then that would be my new y-axis, if you want to think about it like this. So on this one, it's going to shoot up over here, and then it'll decline over there. So there we go. The number e. So you guys might remember that we talked about this last year. So e is going to be approximately 2.718, I think, is the approximation of e. How e is defined is, do you guys remember when we did the compound interest formula? So 1 plus r over n to the nt. So that's your compound interest formula, where n is the number of times your money is compounded per year. And so what e is what if it was compounded every second of every day infinitely? So e is like it's compounded. So like if n was going to infinity, so it was compounded literally all the time. So it wasn't compounded monthly or daily or yearly. It's compounded every second of every day. It just keeps compounding. This is where e comes from. So notice this would become infinity and this would become infinity. And what you end up with is this expression, as n gets really, really big, it gets closer and closer to e, which is 2.718. And so this is called the natural base, because it occurs naturally. So if we wanted to evaluate it, here's a table of values, and here is your e to the x graph. So it looks like a normal exponential graph, but the base is e. So 2.72 is what the book is rounding it to. So they're calling e 2.72. And that's it. So that's what e is. So we can use e as a base. So on Desmos or on your calculator, you have an e button. So typically on a calculator, it looks like e to the x. And on Desmos, you'd have to use the ABC and then use e. So if we wanted to evaluate these, we could. So we would just go to ABC and we could do e. And then we can go back and then we could do e to the 4.2. And there we go. So this would be 66 point, let's go out 3 decimal places, 686. And then e to the -5th, again, e, and we can do the a to the b, and then we want to do square root 5. And there you go. And this would be 9.356. Anything to the 0th power is 1. E to the 1st power was e, which, if we want to get even more exact, e to the 1st power would be 2.7, oh, I was right, 2.718, and then 28, etc. And there we go. If we wanted to graph the following using transformations, so this moved it up 3, this moved it left 2, and this flipped it. So if we wanted to graph this, I'm just going to use Desmos to graph it since I'm already in there. We have negative and then e to the x plus 2 power. Oops, we got to stay up there, so I'm going to put that in parentheses, x plus 2 power. And then get out of the exponent, plus 3. And there we go. So that's what that graph would look like. So it moved my normal guy up 3. So instead of crossing at 1, and then it moved left 2. So left 2, up 3. So 1, 2, 3. And then it was flipped. So normally, right there, and then instead of going up, it's going to go down. So looks about right. So how do we solve exponential equations? So strategy number 1 is you want to try and get the same base. So if you can get the same base, that's going to be strategy number 1. So can you rewrite all of the exponential expressions so that they have the same base? So right now I have 3 and then raised to 3 and then to the x plus 1 power and then 81. So 3 is a small number. So can I rewrite 81 as a base 3? I can. 81 is the same thing as 3 to the 4th. Well, now that I have 3 to a power is equal to 3 to the power, the only way for this to be true is if the two exponential expressions are true. So x plus 1 has to be equal to 4 for this to be true. And so x would have to be equal to 3 for that expression to be true. And if we plugged it back in, 3 to the 3 plus 1 power would be 3 to the 4th, and that is 81. So that works. On the next one, we have 4 to an exponent and 8 to an exponent. I can rewrite those both as base 2's. So 4 is 2 to the 2nd power. And then we still have the 2x minus 1 power. And then 8 is 2 to the 3rd power. And we still have the x plus 3 power. And then you remember when it's in this, you can distribute the exponent. So you can multiply the two exponents. But notice they're both base 2 now. So this exponent, 2 times the quantity 2x minus 1, needs to be equal to 3 times the quantity x plus 3. So 2 times x minus 1 needs to equal 3 times x plus 3 for those expressions at the start to be equal. So we have 4x minus 2 to equal 3x plus 9. Get all of your x's on the same side, and you get x is equal to 11. All right, on the next one, we want to solve e to the negative x squared is equal to e to the x raised to the 2nd power times 1 over e to the 3rd. So we have e to the negative x squared equals, I'm going to distribute this in, and this would be e to the 2x and then over e to the 3rd. Well, what's true here? What can I do with their exponents? Well, they're as a fraction right now, so I can subtract them. So this would be e to the 2x minus 3. So I could subtract the exponents since they have the same base. Well, now I have both are base e, so I can set the exponents equal to each other. So negative x squared is going to equal 2x minus 3. I'm going to get everybody on the same side. I like the x squared to be positive, so I'm going to bring him over. So it'll be x squared plus 2x minus 3 is equal to 0. If I factor that, I get x plus 3, x minus 1. So either x is going to equal negative 3 or x is going to equal positive 1, and that would make that original expression true. All right, well, what if we have something like this? If we know that 4 to the x is equal to 7, then what would 4 to the negative 2x equal? All right, so we know 4 to the x is equal to 7. We want to know what 4 to the negative 2x would equal. Well, how am I changing this expression? Well, I am literally raising it to the negative 2 power, right? So I could rewrite this as 4 to the x and then raise to the negative 2 power, because remember what you do is you can multiply the exponents. But whatever I do to one side, I need to do to the other side. So since 4x is equal to 7, and I want to make it 4 to the negative 2x, I'm going to raise that to the negative 2 power. And then all I have to do is evaluate this side. And 7 to the negative 2 power is 1 over 7 squared, which is 1 over 49. So 4 to the negative 2x power is going to be 1 over 49. Well, if 3 to the negative x is equal to 2, what is 3 to the 2x equal? Okay, well, how do I go from negative x to 2x? Well, I'm going to have to raise that to the negative 2 power, because negative x times negative 2 is going to be 2x. Whatever I do to one side, I'm going to have to do to the other side. So I'm going to raise 2 to the negative 2 power. And 2 to the negative 2 power is 1/4. So 3 to the 2x is going to be 1/4. 9x is equal to 25, and they want to know what 3 to the x would equal to. Well, I'm going to have to rewrite that 9x so it's base 3. So this is going to be 3 to the 2x is equal to 25, right? Because 9 is 3 squared. So 3 to the 2x is equal to 25. So now they're the same base. So to go from 2x to 1x, what would I need to do? Well, I'd need to multiply by a half. So 3 to the 2x, not multiply by a half. I'd have to multiply the exponents by a half. So I'm going to have to raise it to the 1/2 power. Whatever I do to one side, I have to do the other. Do you guys remember what the 1/2 power is the same thing as? If you have something to the 1/2 power, it's the same thing as the square root. So I'm raising something to the 1/2 power. I'm taking the square root of it, and the square root of 25 is 5. So 3 to the x is going to equal 5. All right. So now just a real world use of exponential expressions other than our compound interest formula and half-lives and bacteria doubling problems. Let's say between 9 p.m. and 10 p.m., cars arrive at Burger King's drive-thru at a rate of 12 cars per hour, or 0.2 cars per minute. The following formula from probability theory can be used to determine that the probability that a car will arrive within t minutes of 9 p.m. So the probability that a car will arrive within t minutes of 9 p.m. is given by 1 minus e to the negative 0.2 t. So if we want to determine the probability that a car will arrive within 5 minutes of 9 p.m., so this is going to be, that is before 5 p.m. So within t minutes, so within 5 minutes, that would mean t is going to equal 5, for example, A. So we're just going to plug 5 in. So we want f at 5, and that's going to equal 1 minus e to the negative 0.2 times 5. So what is the probability that a car will arrive within 5 minutes of 9 p.m.? Well, we're just going to do 1 minus e to the negative 0.2 times 5. And it's going to be 0.6321. So there is a 63.21% chance that a car will arrive within 5 minutes of 9 p.m. Part B, determine that a probability that a car will arrive within the first 30 minutes of 9 p.m. So that would mean t would equal 30. So I'm going to plug 30 in. So this would be f at 30 equals 1 minus e to the negative 0.2 times 30. So I'm just going to change that 5 to 30. And I get 0.9975. So there's a 99.75 chance that a car will arrive within the first 30 minutes. So the first 30 minutes after 9 p.m. Graphing f. So if we graph this, we would have 1 minus e to the negative 0.2x. And so that's what it looks like. What does f approach as it increases without bounds? So if I just do this and I start going and we want it to be bigger and bigger and bigger and bigger and bigger and bigger and bigger, what is the y value that my graph is approaching? So what y value does it look like it's approaching? It looks like it's approaching 1. Why does that make sense? So the y value looks to be getting closer and closer to 1. Well, what does this represent? It represents the probability. So the probability is out of 100, right? So the highest that could be is 100%, and written as a number, that's 1. So that makes sense. So if I let that time go on forever and ever and ever, there's going to be a 100% chance that a car will arrive at Burger King. That's what that's saying. All right, gentlemen. Here's your homework. If you guys